I am a principal architect at NVIDIA, where I design programming models and languages for Parallelism in general and for NVIDIA's platform in particular. I've served in leadership roles for several programming languages and standards bodies, including the C++ committee, where I served as the chair of the Library Evolution group. I started programming 12 years ago, and since the start, Parallelism has been my passion and focus. So I'm thrilled to have the chance today to share that passion with you. At the start of my career, I had the good fortune to apprentice under Hartmut Kaiser, who taught me how to think in parallel. And that mindset has been invaluable throughout the years. So by default, we think sequentially. Parallelism is often seen as something that is challenging and complex, a tool to be used sparingly and cautiously, and only by experts. But today, we live in a parallel world. Almost every hardware platform is parallel, from the smallest embedded devices to the largest supercomputers. And so we must change our mindset. Anyone who writes code must think in parallel. Parallelism must become our default. So today, we will focus on one fundamental parallel primitive upon which much can be built, the scan algorithm. And through our exploration of scan, we'll cover key aspects of this parallel mindset that I believe everyone must learn to develop. So a scan takes a range and a binary operator, and for each element, it produces the sum of all elements up to that element. The scan algorithm is sometimes called partial sum or prefix sum. In C++, we have two forms of scan, inclusive scan and exclusive scan. Today, we're only going to be talking about inclusive scan. Now, the output of a scan is a range of the same length as the input, and any binary operator may be used with a scan. We're going to use addition to represent that operator today. Scans preserve the order of input and thus the order of summation. So therefore, the operation does not need to be commutative. So an operation like string concatenation is supported. Now, to parallelize a scan, we must introduce some temporary aggregates, which means that associativity and a left identity value is required. So here's a simple serial implementation of scan, which operates in place. For each element after the first, we compute the sum by adding the prior element to the current element. So let's walk through the computation of a simple scan. So our input here will be a range of 9 single character strings, and our operator will be string concatenation. The first element of the result will be the first element of the input. The second element will be the concatenation of the first two elements. And the third will be the concatenation of the first 3 elements. And then here is the full scan sequence. Now note that the last element of the result is the sum of the entire sequence. This is an important property that we're going to rely upon later. So now, how do we go about parallelizing scan? At first, this might seem like it's challenging because the result of each element depends upon the result for all prior elements. When I approach a parallel problem, I tend to break it down into 3 different components. How will I divide and distribute the work? Today, we'll be dividing into tiles, which are just contiguous subsets of the input sequence. And then next, what calculations need to be performed on each tile of work? And then finally, what communication needs to happen between those tiles? And of these 3, communication is the most important to identify and understand, because communication often dictates how you distribute and what and when you should calculate. So to parallelize scan, we should first consider how it communicates. In fact, I like to think of scan not as an algorithm, but as a communication primitive. So every element of a scan sends information to all subsequent elements. The scan operator will see every single element. Ordering is preserved, so we can reason about relations between neighboring elements. Scans can perform global order-aware reasoning, which makes them very powerful. If every element must communicate directly with every other element in parallel, then we'd have quite the overhead. But as we discussed earlier, we require that the scan operator that we've been provided is associative. And associativity can limit our need for communication because we can divide the problem up into tiles, do a local scan of each one in serial, and then update the local scan with information communicated from other tiles to get the final result. Our algorithm will take two inputs, a range, which will operate on in place, and the number of tiles to divide the range into. We'll launch a parallel for each on the index space of tiles. The body of this parallel for each will be invoked once for each tile and will handle a single unique tile. The number of tiles may exceed the number of threads that the system will use to parallelize this. Within the tile body, the first thing we do is calculate the subrange of the input that this tile is responsible for. We use this range for tile helper function for this. It just divides the input among the tiles as evenly as possible, and then it handles remainders for the last few tiles. Then we take all the elements in each tile, and we perform a local serial scan on them, which we do right here in the code. So next, we need to propagate information between the tiles. The sum of each tile needs to be added to the elements of all preceding tiles. We need somewhere to store this information, one slot for each tile. So before the parallel for each loop, we're going to create a vector. The sum of each tile is the last element of the inclusive scan that we just performed. So we assign that to the applicable slot in locals, which we do right here. Assignments to locals from different tiles may happen concurrently, but that's perfectly fine. Each tile uses a different and unique slot in locals, and no one reads from locals yet, so there's no data race here. Then, after all the tiles have completed their local inclusive scans and written to locals, the result of the scan over locals looks like this. The information that each tile needs to add to its elements is in the local slot for the tile directly preceding it. Next, we need to go parallel again to update the elements in each tile. We skip the first tile because it doesn't need any updates. There are no tiles before it. We perform the update with a serial for each, which adds the appropriate value from locals to each element. We add the locals value on the left-hand side to preserve order. After that addition, we'll have the correct result. So this is a classic, simple, and work-efficient implementation strategy for parallel scan. However, it requires temporary storage on the order of magnitude of the number of tiles, and it has two passes, and thus two global synchronizations. We start in parallel the first part, the upsweep pass, performing the local scans and storing into the locals vector. But then we have a global synchronization waiting for all tiles to complete. Only then can we perform the scan of locals. Finally, we go parallel again, the downsweep pass, to perform the final update. Now, this synchronization comes at a great cost because it decreases the proportion of our code that can be executed in parallel, and it increases the amount of time that we must wait with no other work to perform. This will gravely hurt scalability, impeding performance as we scale up from a single thread to hundreds of threads on our CPUs and hundreds of thousands of threads on our GPUs. Now, two of my guiding principles in parallel programming are to localize synchronization and to hide latency. When we have to synchronize, we must minimize it, only synchronizing with the actors that we actually communicate with. And if we have to wait, we need to find other useful work that we can do while we are waiting. Applying these principles to scan, we must think about what does each tile actually depend on. Does every tile need to wait for all tiles to finish before proceeding? No, we only need to wait for the tiles preceding us to finish. So let's implement scan a second time, this time using a scalable strategy called decoupled lookback. In this version, instead of a vector of temporaries, we'll have a scan tile state object which facilitates communication between tiles. We'll cover how it works in detail later. We'll only have a single parallel pass this time, a parallel for each over all of the tiles. In the body of that for each, we'll compute each tile's subrange as we did before. And we'll perform a local serial scan, just as we did before. But instead of storing the sum of the tile in a vector of locals, we'll pass it to the scan tile state object for this tile by calling setLocalPrefix. We'll look at how this works later. Then, if we're not the first tile, we need to communicate with other tiles to get the prefix that we must prepend to all the elements of our tile. We do that by calling waitForPredecessorPrefix, which returns the prefix. Then we update each element in the tile by adding the prefix from our predecessors to the left. Now let's break down what's actually happening here. Each tile performs its local serial scan and then calls setLocalPrefix, which publishes the information that subsequent tiles need. Then the tiles must wait for the predecessor prefix to become available. While tiles are waiting, other tiles can begin performing their local serial scans and publishing the results, overlapping useful work with the necessary waiting. Eventually, the predecessor prefixes for each tile becomes available. The tile completes, and another tile starts executing. By utilizing oversubscription, that is, having many more tiles than physical threads, we can effectively hide the latency of waiting. But for all of this to work correctly, we need a guarantee that tiles are executed in monotonically increasing order. That is, tile X can only be executed if all tiles preceding X are either executing or have completed. I call this monotonic progress. Otherwise, we could stall forward progress on systems with weak progress guarantees, such as bounded thread pools or GPUs. We could end up with all the physical threads executing tiles that are waiting for tiles that have not yet started, and will be unable to start because there are no physical threads available. To ensure monotonic progress, we have to change how we allocate tile IDs. Thus far, we've been creating a range of integers with iota, and then passing that to the parallel for each. Instead, we'll create an atomic integer and have each tile do a relaxed fetch add to assign a unique and monotonically increasing tile ID. So now let's look at how scan tile state performs the communication between tiles. Scan tile state, it contains a vector of descriptors, one for each tile. The descriptor has two prefixes for the tile: local, which stores the sum of just the elements of the tile, and complete, which stores the sum of all elements from the start of the range to the end of the range. A descriptor also has a state, which is either unavailable, local, indicating that the local prefix is available, or complete, indicating that the complete prefix is available. The state is updated atomically. When you construct a scan tile state, the local and complete prefixes for each tile are default constructed, and the state is initialized to unavailable. Tiles publish the sum of their elements by calling set local prefix, which takes a tile ID and a local prefix. The first tile is a special case. It has no predecessors, so its local prefix is also its complete prefix. We assign the value passed in to both fields of the descriptor. And then we do a store release to set the state to complete, signaling that the prefixes are available. For all other tiles, we set only the local prefix. And then we signal its availability by setting the state to local. Finally, we'll do a notify all to wake up any tiles waiting on the atomic. Wait for predecessor prefix is called by tiles to retrieve the sum of all elements before the tile, which must be added to all of the tile's elements. Wait for predecessor prefix searches through predecessor descriptors, reconstructing a predecessor prefix from the local and complete prefixes of the predecessors. Now, there's three types of prefixes that we're working with here, and so let's go over them to make sure that there's no confusion. Local prefixes are the sum of the elements in a given tile and no other elements. Predecessor prefixes are the sum of all elements before a given tile, excluding the elements in the tile itself. Now, predecessor prefixes are returned from wait for predecessor prefix, but they're not stored in the descriptor. Instead, they are constructed on the fly. And complete prefixes are the sum of all elements from the beginning of the range to the end of the tile. A complete prefix is just the sum of the predecessor prefix and the local prefix. So let's work through this in an example. We're going to scan a vector of strings with string concatenation. We'll divide the input into 4 tiles of 3 elements each. We start with a local serial scan of each tile, which will produce this. The local prefix for each tile is the sum of all of its elements, which is the last element of the local scan. The predecessor prefix for each tile is the sum of all preceding elements. So for the first tile, that's nothing. For the second tile, that's the sum of the first tile, which is ABC. For the third tile, it's the sum of the first 2 tiles, A, B, C, D, E, F. And then for the fourth tile, it's the sum of the first 3 tiles, A, B, C, D, E, F, G, H, I. And then the complete prefix of each tile is the predecessor prefix plus the local prefix. And so now that we understand what these prefixes are and how we compute them, let's look at wait for predecessor prefix itself. Now, to construct the predecessor prefix, each tile will search the descriptors of the tiles preceding it, starting at the tile directly before it and moving backwards towards 0. For each preceding tile, if its state is unavailable, then we wait. If its state is local, then we add its local prefix to the predecessor prefix and we continue searching. If its state is complete, then we add its complete prefix to the predecessor. And once we encounter a complete prefix, we can stop because a complete prefix incorporates all information from the start of the range up into the current position. This is why we call this algorithm decoupled lookback. Each tile searches backwards from its position, and each tile searches independently. Independent searching is important because some threads may see publications of prefixes before other threads, allowing them to make further progress, and it removes a dependency between all of the threads. Now, let's look at the implementation of wait for predecessor prefix. We begin by default constructing a T, which we will sum the predecessor prefix into. Next, we loop from I minus 1 to 0. For each preceding tile, we do a wait acquire until its state is not unavailable. This establishes a synchronizes with relationship between the store release in set local prefix. After the wait, we load the state again. We know that the state will no longer be unavailable because states are only ever set as available during unavailable during initialization before the critical section. So at this point, the state is now either local or complete. If the state is local, then we add it to the predecessor prefix that we're building. Remember, we must sum it from the left to preserve order. Otherwise, if the state is complete, then we sum it into the predecessor prefix and we stop the lookback because the complete prefix covers all elements from 0 up until the current position. So we're done. Once we finish building the predecessor prefix, we must compute and publish our own complete prefix. We compute it by summing the predecessor prefix with the local prefix. We signal its availability with a store acquire of complete to our state and a notify to wake up anyone waiting on our state. Now this synchronizes with the wait earlier in this function, ensuring that if a thread observes the state is complete, they will also see the write of the complete prefix. Finally, we return the predecessor prefix. So let's work through another example. Here's a snapshot of a scan execution with 8 tiles. Let's perform wait for predecessor prefix for tile 3. We start by looking at tile 2, whose state is local. We sum its local prefix into our predecessor prefix. Next, we look at tile 1, whose state is local. Now notice here that tile 1 has actually written its complete prefix, but we haven't observed the state change yet. Its status is still local, so we can't actually use it even though that thing has temporally already happened. It's not visible to us under the memory model. Instead, we sum its local prefix into our predecessor prefix. Finally, we look at tile 0, whose state is complete. We add its complete prefix to our predecessor prefix, and then we finish. Next, we compute our complete prefix by summing the predecessor prefix and our local prefix. We write it to our descriptor and set our state to complete. Next, let's do tile 5. We start at tile 4, whose state is local. We sum its local prefix into our predecessor prefix. Then we look at tile 3, whose state is complete. So we sum its complete prefix into our predecessor prefix, and then we finish. We get to finish early here because we found a complete prefix. Finally, we calculate our complete prefix, and we store it to our descriptor and update our state to complete. And that's it for scan tile state. Now we should have an understanding of how we perform communication in this decoupled lookback scan. Our decoupled lookback implementation needs only O tiles storage, while our 2-pass implementation needed O input storage. For context, for my benchmarks, I ran with 4 billion elements and 1,000 tiles. So it's much better to be in the O tiles regime than the O input regime. Our decoupled lookback implementation is single pass, requiring only 1 global synchronization, while our 2-pass approach needed 2 global synchronizations. Now in benchmarking, I observed this decoupled lookback scan performing 3 times faster than our 2-pass scan on a 64-core CPU system with a 4 GB problem size. At GPU and distributed scale, decoupled lookback will outpace the 2-pass approach even more. All right, so as we said, we looked at how we implement scan, and as we said, scan is a building block. It's worthy in its own, but its importance really lies in what we can build with it. So there's a lot of problems that have a summing, a counting, filtering, searching, or neighbor-aware aspect that can be solved with a scan. And we're going to look at 2 examples today, and the first one is copyIf. So copyIf takes an input range and a unary filter operation. So as an example, here we've got a range of characters and a function that returns true for characters that are letters. So it produces a range that contains only the elements of the input for which the filter operation is true. CopyIf cannot be evaluated for each element in isolation. To determine the correct place in the output to write an element, we must know how many elements before it will pass the filter. And so that, to me, sounds like a scan. So we'll start off with a simple implementation. Our copyIf function will take an input range, an output iterator, and a filter operation. First, we're going to create a vector with a flag for every input element. Then, in parallel, we will evaluate the filter operation for every input element, storing the result in the flags vector. Next, we're going to do a scan of this flags array with integer addition as the operation and integers as the output. This is called a plus scan. We'll create storage for the output of our plus scan. We need 1 integer for each element, plus an additional integer for the final count of how many elements we've copied. And just trust me on that for now, that part will become clear in a moment. So next, we do a parallel scan of flags into indices, starting at the second element of indices. The first element of indices has been default initialized to 0, which is always the correct output index for the first element. We write into indices offset by 1. Let's take a look at an example to understand why. Let's build the indices vector for this problem. By fiat, index 0 is always 0, because we're going to always write out to 0. We offset the output by 1, because when we encounter an element that is true, we output it at the current index, and then we bump the index for the next element that we write. A is a letter and will be written at index 0. And so therefore, the next letter will be written at 1. So the second element of indices is 1. B is also a letter and will be written at index 1. The next letter will be written at index 2. So then we have 2, which is not a letter, and so it will not be written, and thus the index is not incremented. Likewise, 3 is not a letter, and the index is not increased. And the same is true for 4. But then E is a letter, and it will be written at index 2. And then the rest of the indices is scanned in a similar fashion, producing this. Now we perform the next step, where we walk through the vectors, the flags vector, and for every true flag, we write that element at its associated index. We call this the write pass. So A is written at index 0. B is written at index 1. E is written at index 2. And G is written at index 3. And the final element of indices has the count of how many elements were written, which is 4. So let's look at the write pass in code. It's a parallel for loop that iterates the input, flags, and indices. So for each element, if the flag is true, then we write the element at the associated index. To calculate the bounds of the subrange that we return, we use the last element of indices, which gives us the count of how many elements were written. And with that, we have a parallel copy implementation. Now, this implementation needs a lot of temporary storage, on the order of magnitude of twice the size of the input. It also uses 3 parallel passes, which means we have 3 global synchronizations, 2 of which we'd hope to avoid. Now let's improve this with decoupled lookback. Now we need to take a tile size in addition to our other parameters, as we're going to be tiling up the input. We need a scan tile state for indices and an atomic to assign tile IDs. Next, we've got our tile loop. In the body of the loop, we assign the tile ID and calculate the tile's subrange, just as we did in the inclusive scan decoupled lookback implementation. Next, we'll create tile local storage for flags, 1 for each element in the tile, and evaluate the filter operation into the flags. We're dynamically allocating this storage on the fly here, but it could also be pre-allocated depending on how many physical threads we have, or it could be statically sized and on the stack, which would require static tile sizes. And that's how we'd actually do it on the GPU, with static tile sizes and with like static thread storage. Here, we'll create tile local storage for the indices as well. Then we'll perform a decoupled lookback scan of flags into indices using set local prefix and wait for predecessor prefix. We'll output into indices offset by 1, just as we did in the 3-pass copyif. Next, we do the write pass. And then finally, we return the subrange of elements that we output using the last tile's complete prefix, which has the final count of elements written. And now we have a much better copyif implementation. It only needs O of tiles storage instead of O of input storage. Now remember, in my testing, I was using billions of input elements and thousands of tiles. Now in my benchmarking, I observed that this decoupled lookback copyif performed about 11 times faster than that 3-pass copyif on a 64-core CPU system with a 4 GB problem size. So now let's move on to the climax of this talk, an algorithm that I think is really truly beautiful, chunk buy. So chunk buy takes a range in a binary comparison operation. It splits the input into subranges in between each pair of adjacent elements for which the comparison operation returns false. So its output is a range of subranges. In the example shown here, we have text with new lines and an operation that returns true if the left-hand side is not a new line. So this will split the text into individual lines, each one terminated with a new line. Let's look at another example. So we've got a range of 9 characters and the equality operation. For the first 2 adjacent elements, the operation returns false. For the next 2, it returns true, and then false, and then true, and then true, and then false, and so on. And so we can see from this that we have 4 splits and 5 chunks that we need to form. So how do we go about parallelizing this? There's 3 pieces of information that we'll need. First, we need to know what index is this chunk in the output. How many chunks came before it? This is similar to copyif. Next, we need to know where each chunk starts. And then finally, we need to know where each chunk ends. So we'll define a data type that will track all this information for each element. And we're going to call it interval for reasons that will become apparent. And this interval struct will have 4 members. A flag, which has the result of applying the comparison operation. It is false if there is a split between this element and its neighbor to the left, and it is true otherwise. We need an index, which indicates where the current chunk should be written in the output. This is going to be a plus scan of the inverse of flag. Both flag and index are calculated in a similar fashion to copy if. Then we need a count, which keeps track of how many elements are in the same chunk. All the elements in the chunk will have the same index value. And then finally, we have end, which is simply a running count of how many elements we have in total. And this gives us the position of the current element. So next, we need to define how we sum intervals. Think of an interval as an aggregate of three summed components: index, count, and end. So its sum operation must perform three separate but related sums. We don't sum flag. Flag is set by the comparison during the initialization of the range of intervals. When adding two intervals, we always take the flag from the right. Index is initialized to the inverse of flags, and then we just plus scan it. Count is a little bit trickier. It tracks how many elements are in the current chunk, so it needs to be reset whenever the current chunk ends. We can tell the current chunk ends when the index changes, and that happens when the right-hand side is non-zero. Finally, for end, we just do a plus scan. End will be initialized to 1 for every element and to 0 for identity objects. Suspend disbelief for now. We're going to work through an example that will demonstrate how all of this works, and that'll make it a little bit clearer. So our chunk by algorithm takes an input range, an output range, and a comparison operation. And we're going to start off by writing a simple multipass version. So we'll need a vector of intervals, one for each element, plus an additional one for the final count of how many chunks we have. This is similar to what we needed for copy if, just with intervals instead of indices. Next, we need to initialize the intervals. We'll start off by initializing the interior points of intervals, everything except the first and last elements. We do this initialization in parallel. For each interval, we have to look at two adjacent elements, as our comparison operation must be applied to two elements. An interval always represents the element on the right-hand side of the operation. We also need a special identity value on the left to handle the first element, and a special identity value on the right to close the last chunk and give us the final count of how many chunks we have. We'll handle the identity values here. For each interior point, we first evaluate the comparison operation. We set flag to the result of that comparison, and we set index to the inverse of that. We initialize both count and end to 1, as this interval represents a single element at this point. For our example problem, the initial state for the interior points looks like this. For the first element, the left identity, we set flag to true because it does not represent the end of a chunk. And we set index to 0 because that's the index that we'll start writing to in the output. For the right identity, the last element, we need to end the last chunk. And so we set flag to false, which split. And we set index to 1, which indicates that this element does not belong to the same index as the prior element. With the addition of the special identity values, we have our completed initial state for intervals. So next, we do a parallel scan of intervals. So let's walk through that for our example problem. So first, we're going to handle index. We just plus stan index, which starts off as the inverse of flags. And so we end up with this. This is quite similar to what the scan for copyif looks like. Next, we scan count. And remember, count gets reset whenever the index changes. So for the first element, the output is the same as the input, 1. For the next element, the count gets reset because the index has changed. The index on the left is 0, and the index on the right is 1. For the next, the count increases because the indices are the same. For the next one, we're going to once again reset the count. The indices are equal for the next element, so the count is increased. And likewise for the element after that. And we proceed in this fashion for the rest of the elements, producing this. Finally, we need to handle the scan of end, which is a bit simpler. This is just a plus scan with no reset, which results in this. And this is what we'll have in the intervals vector after our scan. So next, we have the right pass, where we need to use that information that we've built up in intervals to produce the chunks. This right pass is done on adjacent intervals, which is different from what we did for scan and copyif. If the flag of the right interval is false, then it represents the end of a chunk. The right interval represents 1 past the end of the chunk. The last element in the chunk is represented by the interval on the left, so that's what we would use for the right. We write to the index specified by the left interval. We write a subrange, constructing the indices of the beginning and ending using the interval's end and count members. Range indices are half closed in C++, so the ending should be the index 1 past the end of the last element. Interval.count has the count of the elements in this chunk, and end has the index 1 past the end of the current element. So the index 1 past the end of the subrange is just the interval's end member. And the beginning of the interval is the index 1 past the end, which is interval.end, minus the count of elements in this chunk, which is interval.count. So here's what the constructed subranges look like for our example problem. We have 4 splits producing 5 chunks, and we have 5 false flags, 4 from the splits and 1 from the right identity. So the first chunk starts at 0 and ends at 1 with a length of 1. The second chunk starts at 1 and ends at 3 with a length of 2. The third chunk starts at 3 and ends at 6 with a length of 3. The fourth chunk starts at 6 and ends at 7 with a length of 1. And the fifth and final chunk starts at 7 and ends at 9 with a length of 2. Finally, we return a subrange of all of the chunks that we wrote. We get the count of how many chunks we have from the last interval's index, similar to what we did for copyif. In the case of our example problem here, it's 5. And that's it. We have our chunk by algorithm. And as with copyif, this requires O of input temporary storage and has 3 global synchronizations, which is not ideal. So let's quickly rewrite this with decoupled lookback. So this time we're going to take an additional tile parameter, as we're going to now be tiling. We'll create a scan tile state of intervals and an atomic to assign tile IDs. And as with all our other decoupled lookback algorithms, we'll have a single parallel for each over the space of tiles. Each tile determines its tile ID via the atomic. Because many of our calculations are performed on adjacent views of ranges, and we must add special identity values on the left and right, we must treat the first, last, and interior tiles differently in a few different places. And so we're going to define 3 bools to classify what kind of tile we have, whether we're the first, last, or an interior tile. Next, we'll calculate the subrange of elements that belong to this tile. For the first tile, we'll skip the first element, which has no neighbor to the left. Recall that we did this in the multi-pass version by offsetting the output of our scan by 1. Next, we must initialize the intervals, just as we did in the multi-pass version, except this time we do it locally in serial in each tile. For the interior tiles, we need 1 less interval than we need for the first and last tile. This is because the first tile has the additional left identity, and the last tile has the additional right identity. They are initialized here if we're in the applicable tiles. Next, we initialize interior points. For the first tile, we start off by 1 to skip over the left identity. The initialization of the interior points is done just as it was in the multi-pass version. Next, we perform a decoupled lookback scan of intervals with a local serial scan, set local prefix, and wait for predecessor prefix, and an update pass, just as we've done in our earlier examples. And then finally, we have the right pass over adjacent intervals. This works just as it did before. If the flag on the right interval is false, we write out the chunk using the information from the left interval. And finally, we return the subrange of all chunks using the complete index of the last tile to get the count of how many chunks we wrote. And that's all there is to it, a parallel and scalable single pass chunk by algorithm. It only needs O of tiles storage and a single global synchronization. And in my testing, I saw it would be about 9 times faster than that 3-pass version that we saw before. So these are just a few examples of what we can build with scan and decoupled lookback mechanisms. They can be used to solve all sorts of problems such as summing, counting, filtering, searching, sorting, and many more. But our purpose today was not necessarily to teach you about scan in particular. It was to show you the thought process of how we go about parallelizing an algorithm like scan. There's 3 key principles that I'm hoping you'll take away from today's talk. The first is to focus on communication because it's going to dictate everything else about the design of a parallel algorithm. Next, you need to localize synchronization and avoid global barriers because they reduce scalability and performance. And you need to find a way to overlap weighting with useful work to hide latency. And if you want to learn more about parallel programming and algorithm design, my buddy Connor and I have a podcast, ADSP, Algorithms Plus Data Structures Equals Programs, available on all streaming platforms. And you can go subscribe now. And also, we've got lots of great courses in NVIDIA's Deep Learning Institute on C++ and parallel programming. And there's a couple new courses that are going to be released soon. And as a thank you for attending today, you can access our course catalog for free for the next 6 months using this QR code, and you can pick one course to get free access to. And that's pretty much it. So now we can move on to questions. I should give a thanks to my co-host Connor, who contributed to the development of this talk, and also David Olson, Dwayne Merrill, Jared Hobrick, and Michael Garland, who are all my coworkers and did work on some of the foundational algorithms that I talked about today.
Yes, thank you for the great talk, Bryce. There has been one question throughout the talk, and that's towards namespace stdv, stdr, stde, and
stdv. Yeah, so stdv is just stood views, str is just stood ranges, and ste is just stood execution.
Yeah, I think we just
gotta have stuff fit on the slides.
Yeah, I thought that. And it makes sense to use them also in real life if you don't want to type that all the time.
Yeah.
So if you have any questions, post them to the Q&A tab. That's the best way. Then people can rate them, and I have easier tab to choose. Also, if you're listening on LinkedIn, just put it in the chat, and then I'll be able to display it. And let's see what questions are coming up. One question we had during the talk also was the standard. What standard are you using in this code?
Let's say, I don't think you need anything beyond C++ 17. I mean, and we use ranges in a few places, but you could choose to not use ranges. So you could do it in C++ 17 or C++ 20. There's nothing super new or fancy there. There's a couple of like newer features that are used. I suspect I probably compiled this code with C++ 20. It's easy enough to check because there should be a note there. Oh, it doesn't say.
Yeah.
But yeah, I would guess I compiled it with C++ 20.
And yeah, so I think like similar frameworks are available if you're not using like C++ 20 or 17, or if your range is available. But
yeah, you could use Thrust for a lot of these things, but
yes, right.
I suspect that even NVIDIA's platform will move to being C++ 17 as the default at some point.
Oh, you're saying you're not on 17 yet, NVIDIA?
No, we are not yet on. I mean, I think 17 is supported, but it doesn't mean we still support older standards. At some point, we will not support anything older than C++ 17.
Yeah, I think there's a question in the chat about the slides. They will be shared. There is probably there is a question. Let me quickly copy that is visible. So is the parallelism done in CUDA or just a general purpose processor?
No, this is just C++ standard parallelism. So it can use whatever the backend is that your platform supports. So all these examples, I ran them all on a CPU with just whatever the default backend would be, which in the case of NV C++ would be based on our OpenMP runtime. But you could also run this code on GPU. You could run it anywhere on whatever parallel backend you want, because it's just C++ standard parallelism.
True. And so what for parallelism was used as the parallel algorithms, as far as I saw.
Yeah.
There's a question about CUDA. Just fair disclaimer, I'm not sure if Bryce is a CUDA expert, but will CUDA eventually get
malloc-free? CUDA is the main thing I work on.
Okay.
Well, that's kind of a complicated question because I'm not really sure what they mean by that. I mean, CUDA has its own mallocs and free APIs, CUDA malloc and CUDA free. I'm not sure. I guess I'm not really sure what the ask is here. We have our own allocation APIs that are raw memory type APIs. We also have new and delete type APIs in things like Thrust and in our modern CUDA C++ interfaces. But I'm not. I guess I would need to understand better what this person means because it's not clear to me from the question.
Yeah, I think that you provide ways to not use that in user code, right?
What do you mean?
Well, are you forced to call malloc on free when you write code for CUDA, etc.? I think with Thrust, etc., you have frameworks that this up, right?
So again, this is like if they're talking about like stood malloc and stood free, that's different from CUDA's, internal or CUDA's own memory allocation APIs, of which there are both low-level and high-level ones. There's Thrust has object creation and destruction routines, but for the most part, when you're moving things between CPU and GPU, the only way that it's just like, sending information over a wire, your data has to be able to be formulated as, plain old data. I mean, unless you put it into unified memory, in which case then the object doesn't actually move between CPU and GPU. But if you're doing a copy between CPU and GPU, it's going to be some form of byte-wise copy.
Yeah.
But I guess I would be interested in hearing what the person's means by this question or what they're trying to accomplish, because I don't know that the answer to this question is going to be meaningful without understanding that.
Yeah, I can see that. Let's see. So yeah, let me add to that. Yeah, they were referring to CUDA malloc and CUDA free, and of course, yes, C++ encourages not to use malloc free on new delete. So
yeah, I mean, you can use things like the CUDA C++ core libraries that have higher level APIs. I mean, Thrust has CUDA allocators that you can use with unique pointer, and it has allocate unique facilities. But like this would be like asking, it would be like asking like Linux, are you going to ever get rid of malloc and free and only have new and delete? And the answer is, of course not, no, because they're lower level facilities that you need to implement the higher level things.
That's true. There was a question on GPUs. What is a good way to try something like this? I'm not sure what this means. Like probably what you talked about in the talk, without GPUs available, something like a test environment.
Well, first of all, I mean, almost anybody can get access to GPUs. If you just have like a Google Colab, like Google Colab has, I believe, free, like it's like a Jupyter Notebook-like environment, and it has free, L4, which is lightweight GPU instances. So like, I'm pretty sure that if you want to just write some like GPU code, that there's plenty of free resources out there. They're not going to be like, compute heavy GPUs, and you wouldn't be able to run stuff for a long time. But if you just want to play around, something like Google Colab, I believe, should allow you to do that. I'm not positive about that. I know I have Google Colab and I can use GPUs there, and I'm pretty sure I just had to go and change some setting. But if you mean something like this, like standard parallelism, you can run it anywhere. I mean, you could take the code that I wrote and ran it on your laptop. But I don't think that like for testing around and experimenting with code, getting access to some GPU environment shouldn't be that hard. There's lots of online platforms and environments, some of which that have free trials or free access to lightweight instances.
That's true. And when your testing environment does not have GPUs and your code gets GPU heavy, you maybe should think about adding one and adding access. Because like testing that on GPU code, it's possible, but not really bringing you the results. Okay. So the 3 criteria you talked about, Bryce, there's a question. Are those 3 criteria, like, is it almost always applicable to parallel thinking?
By By the 3 criteria, do you mean the 3 criteria for how to think about your problem of thinking about, how do you distribute your data? What are you calculating and how you communicate? The answer is yes. Or did you mean the 3 key principles that I gave at the end, which was, hiding latency, avoiding global synchronization, and let's see, what was the third one? And focusing on communication. Yeah, those are also all, I think, applicable in pretty much any parallel programming environment. I mean, there's some situations in which you don't want to hide latency, because hiding latency can often mean that you end up doing work inefficient strategies. So there's the theory of parallel compute, at least at scale. Usually you're willing to sacrifice efficiency for parallelism. So you duplicate some work because it allows you to get to a faster time to solution, even if it's less efficient because you're doing more work. There are certain environments in which that is not, what you want to do. But I mean, generally speaking, when we're talking about data center side compute, these are the things that you want to be doing. There's a difference between being efficient and going fast, and parallel computing is about going fast.
All right, so there is I think a general question about the parallel algorithms. Maybe we should quickly talk about what kind of the backends are and how you can actually switch between them and.
So I mean, the backends that are going to be available is going to depend upon what compiler you're using. With the NVIDIA HPC compiler, you can do -stdpar equals multicore to use our CPU backend, which is going to be based on our OpenMP runtime. Or you can do -stdpar equals GPU to use our GPU backend, which is based on Thrust and Cub and CUDA. We may have other backends in the future. For LLVM, Clang and GCC use the same parallel algorithms backend that is called PSTL. That's a project of LLVM, and it has its own backend mechanism. I think it may be define based to switch between them. So you pound define something. MSVC just has one backend that I know of. So it just depends on what your platform has available. The design of the standard parallelism, you cannot, at a fine granularity, pick which backend. So you can't say for this one algorithm call, I want to use this backend. That's what we're hoping to introduce with C++ schedulers that are in C++ 26, where you'll be able to have finer grained control over where your code actually runs. And if you watch some of my talks on C++ standard parallelism, I talk about some of the limitations of the parallel algorithms. And the 2 main ones is that they're not asynchronous and that they don't allow you to control exactly where things run, that they just run on some implementation defined, backend. But in the future, you'll be able to control that with schedulers.
That's true. We have a whole different set coming up for parallelism with the future in 26.
Yeah.
And for the moment, that's it, what I see in questions. I've pinned the link to the learning platform from NVIDIA where you can claim your free course. And I see, there is, no, this question we already had. And let me see if there's something coming up from, no, nothing from LinkedIn. So seems we are for now through with the question. If you have any more questions, we might have some time for that. But I think we're pretty much done with that. So thanks for the talk, Bryce.
Yep,
And
my pleasure.
let's see. Yeah, so I have probably the ability to bring the... there's a question on the courses, and I'm not sure if... so the link brings you to this course page, and there's a question if there are student discounts for NVIDIA courses.
I think there might be. I don't know.
Yeah,
but if you want to send me an email, my email's in the slides, and I can forward your question to the right people.
Yeah. Shall we bring up your slides again? I see you already stopped sharing. But generally, that's also something I will talk to with Irina and give you feedback on that. That's actually a good question. So there's a question like, from what time are the courses available? Those courses are already available, to my understanding. So
yeah, they're not live courses. They're like pre-recorded courses that you can go and download and labs and stuff.
Right. These are
So
all
they're on
online,
demand,
which you can take on your own pace and time.
We do have in-person trainings at certain events, like at GTC in March. We have DLI courses taught in person the weekend before, and I think also at some other conferences. GTC is the only one that I know about. But if you're interested in learning more about CUDA or GPU programming, GTC is a great conference to come to. We've got a whole track just on CUDA development this year, which is a new thing. We're very excited about it. There's going to be a lot of new content on that, some new DLI courses, some tutorials. So that is in March. I think March 17th to the 21st in Silicon Valley.
And online. You can follow.
Yes, and online too.
GTC online for free, which is also a great way. And yeah, so with a link, you get a full course for free. So if you're a student, and even if you're like not available to have the other courses, that's already a good start for you. You get a course for free. And then, yeah. And I think that's it for today. Thank you for coming, Bryce.
Okay. Yep, my pleasure.
But, anything else about NVIDIA which we need to know?
Nothing comes to mind.
Good. Then thank you to NVIDIA for sponsoring today, and thank you, Bryce, for bringing this great talk, which actually almost made it to the conference. But then we only give like one talk per speaker.
Yeah.
And
they liked the other talk better, but I'm glad we were able to give this one.
Yeah.
Okay.
All right.